Hello class. Last class we discussed about Bohr's theory, and after that we discussed about what are the drawbacks of Bohr's theory, and the last topic was Heisenberg uncertainty principle. Now today we are going to discuss about a very important topic, that is quantum numbers. Okay, quantum numbers. Before that, I want to make you the difference between orbit and orbital. Okay, orbit and orbital. So orbit, as we know, it is a well-defined circular path around the nucleus in which an electron revolves. Whereas orbital is defined as a region, or it is a space in three-dimensional around the nucleus where the probability of finding an electron is maximum. So it is the region where the electron finding probability is maximum, whereas orbit is a well-defined circular path around which the nucleus in which the electron revolves. Next difference is orbit is circular in shape, whereas orbital we have got four orbitals like S, P, D, and F orbitals. Okay, we'll be using these frequently, S, P, and D orbitals, and explain you what are they. SP and D orbitals are spherical. P orbital is dumbbell and D orbital is double dumbbell shaped. Okay. Orbit represents an electron moves around the nucleus in one plane, whereas orbital represents an electron can move around the nucleus in three-dimensional space, that is along x-axis, y-axis, or z-axis. Orbit represents the position as well as momentum of an electron can be known simultaneously with certainty. It is Heisenberg uncertainty principle. So, whereas in case of orbital, it represents that position as well as momentum of an electron cannot be known simultaneously with certainty. It is in accordance with the Heisenberg uncertainty principle. And the last difference is, in orbit, the maximum number of electrons in an orbit is 2n square, where n is the number of orbit, whereas the maximum number of electrons in an orbital is 2 only. It can accommodate only 2 electrons. Now we will come across a very important topic, that is quantum numbers. Okay. Quantum numbers are the index number which are used to specify the position and energy of an electron in an atom. So quantum numbers are that numbers, you can call this index number, which will define the position and energy of an electron in an atom. Say for example, to identify a person, just as a person is identified by its address, an electron in an atom is completely known by specifying the quantum numbers. And we have got 4 quantum numbers. Each one of these have specific values which are interrelated, and they give the complete picture of electrons, about their position, energy, and the shapes of the orbitals where they are present. Okay. Now we need to see these 4 quantum numbers. The 4 quantum numbers are, number 1 is principal quantum number, denoted by small n. The second is azimuthal or orbital quantum number, denoted by small m. The third is magnetic quantum number, denoted by small m. And the fourth one is spin quantum number. Now we need to discuss about all these 4 types of quantum number individually and try to understand what are they. So first we are going to discuss about principal quantum number n. Okay, what is it? This quantum number, designated as n, gives the number of major energy level or orbit to which the electron belongs. So this quantum number, principal quantum number, defines the main energy level, or it is the number of cell or orbit that is present for an electron. It can have any positive whole number value excluding 0. So this n cannot be a 0. It will have 1, 2, 3, and it goes on up to infinity. Now, the information that this principal quantum number gives us. Number one is the value of n represents the cell which are designated by capital letter K, L, N. Say for example, if the value for n is 1, then it is the first cell, that is K cell. If the value for n is 2, then it is L cell. If it is 3, then N cell. 4, N cell. Okay, so it represents the number of cells, we can say. The principal quantum number also helps to determine the average distance of the electron from the nucleus. Next, n also determines the energy of the electron in orbit. So n values can also determine the energy of the electron in a certain orbit. And n value can also be used to calculate the maximum number of electrons that a cell can hold or accommodate. So maximum number of electrons in an orbit with principal quantum number n can have 2n square electrons. Okay, this is the general formula. Say for example for k, when n is 1, so when you just put the value for n equals to 1 in this, it becomes 2 into 1 square into 2 will give you 2. For L cell n equals to 2, the value will get is 8 electrons. Similarly, when n equals to 3, we get 18. N equals to 4, we'll get 32. So it can give you the maximum number of electrons as well. Next quantum number is, we can call azimuthal, subsidiary, orbital, or angular quantum number. This has got various names. So we just take it as this azimuthal or orbital quantum number denoted by L, small l. Okay. Now, the value of L depends on the value for n. So this orbital quantum number depends on the value of principal quantum number. Say for example, for a given value for n, that is principal quantum number, n can have values from 0 to n minus 1. Say for example, let us try to understand with the help of the example, it will clear you more. Say for example, when n equals to 1, then what will the value for L? So according to the value for L ranges from 0 to n minus 1. So 0 to n. So the value for n is 1. The value for n is 1. So n 1 minus 1, that will be 0. That means for n equals to 1, the value for L will be 0. Similarly, for n equals to 2, the value for L will be 0, and when you put the value for n equals to 2, it becomes 2 minus 1, that is 1. So you can have two values, 0 and 1. Okay. Similarly, when n equals to 3, we can have three values, 0, 1, 2. Okay. Now, over here, when we have got the value for 0, L equals to 0, L equals to 1, L equals to 2, they represent a certain orbitals that we have to remember. Please make note of this. Say for example, if the value for L is 0, then it is S orbital. If the value for L is 1, P orbital. If the value for L is 2, D orbital. And if the value for L is 3, F orbital. So we'll consider only these four orbitals, S, P, D and F. Okay. So for example, from here we can see, when n equals to 1, the value for L will be only 0, as we have seen in that, because L ranges from 0 to n minus 1. And over here, since L equals to 0, from the above table, it belongs to S orbital. So S 0, 0, S, and this one is for this. Okay. Similarly, when n equals to 2, the value for L is 0 to n minus 1, so we can have two values, 0 and 1. So for 0, as we know, L equals to 0 means S orbital. And since over here principal quantum number is 2, it becomes 2s. Okay. And the value for L equals to 1, it is P orbital, so it becomes 2p for 1. Similarly, when n equals to 3, it will be 0, 1, 2, 3. This will be S, P and D. Like that it goes in, okay. So, and one more thing that you need to know is, what is the maximum number of this electron present in this orbitals s, p, d and f. So in case of s orbital, just remember this is also very important. S orbital can when value of L is 0, as we know the subshell is S and the maximum number of electron it can accommodate is 2. Next, when value of L is 1, it is p orbital and the maximum number of electron it can accommodate is 6. For D 10, for F 14. So S2, P6, D10 and F14. This will be using frequently. After this we have got a topic called electronic configuration. So at that time or where or to understand other important laws and principles will be coming across this number, the maximum capacity of the 4 orbitals. Okay, just make a note of that.